Hello there, you're once again welcome to your favorite YouTube channel, the Aerospace Engineer. And for today, we'll be looking at an introduction to differential equations. I hope you're ready. Okay, so first and foremost, we'll be looking at a definition of differential equations. What at all are differential equations? So we have a very simple definition over here. It's an equation involving derivatives of a function. Okay, so normally it's an unknown function, so we solve to find the unknown function. So we have an illustration of what a differential equation looks like, because you like to know what it looks like at all. Okay, because you've been familiar with algebraic expressions, okay, equations which are in the algebraic form, but then we have this differential equation. So this is a form it takes. So we have y prime. Okay, so the prime notation is actually to indicate that it's a derivative. Okay, so and then we have a plus 2y. Okay, so the y over here, okay, is actually the unknown function. The function will be finding. Okay, so its derivative plus 2 times the function equals x squared, where x is the independent variable. Okay, it's the independent variable. So explicitly we can put it in the form of y prime of x plus 2 y of x equals x squared. Okay, so as I might have already indicated or hinted, okay, we have the y prime of x, y prime of x, and subsequently to the end derivatives, okay, of the function y of x, okay, to be illustrated or to be represented in this form. Okay, so we also have the y of x as the function, as I've already entered, and then x is the independent variable. Okay, so we'll move on in our introduction. We go on to applications. Okay, so looking at applications, I hold one principle that, you see, when you know why you are doing something, you're able to do it better. Okay, or you're able to do it with more zeal. Okay, so this is just to tell you that the course you are learning, or the introduction you're having, okay, is something that is really important. It will help you in various aspects of whatever you want to do. So these are some simple applications. Okay, so we have the Newton's second law of motion, as you might have known already. Okay, so force equals mass times acceleration. Okay, so this is actually a differential equation. How do you get to know? Okay, so we have force equaling mass times acceleration, that's A. Okay, but then our acceleration equals differential, okay, or derivative of velocity with respect to time. So it's a derivative. Okay, so we can write this also as force equals mass times, so let's say we put it as v prime. So we have our derivative here because it's an equation involving a derivative. Okay, but then you can go ahead to represent acceleration as d squared s over dt. Okay, so then we now have acceleration to be s prime prime. Okay, so force can now be represented as force equals mass times second derivative of displacement with respect to time. So we can put the time over here. So isn't it very simple? Yes, it is. Okay, so this actually to show you that the Newton's second law of motion is a differential equation. So back to our application. So we can also have population growth statistics. So you probably have heard of population census, how to predict the population of any group of living organisms or anything at all you want to analyze. Okay, so differential equations actually help us in doing that. Okay, so we also have earthquake analysis, okay, where we look at the vibrations in buildings as a result of earthquakes. We can analyze. Okay, so we also have simulations and animations, various movies. Okay, you see the explosions and then sort of waterfalls, okay, that we might see in various animated movies, okay, are not real. Okay, they are simulated, and then, for instance, using Navier-Stokes equation. But then these differential equations help us in what in doing the simulations. Okay, so I hope you're okay with the applications, and then your morale is boosted for differential equations. So let's go ahead. Okay, so we have classifications. You see, differential equations is a broad aspect. Okay, and for us to be able to analyze it very well, we have to break it into classes. We have to classify them so we can address them very well. Okay, so we have classification, okay, in various classes. Okay, so we can classify differential equations according to the type. Okay, so in this case we have ordinary differential equations or partial differential equations. Okay, we have classification according to linearity, okay, where it can be linear or non-linear. Okay, then we have classification according to the order. Okay, so we have first order differential equations, second order differential equations, still nth order differential equations, and then we also have the degree. So it can have a degree of 1, 2, 3, or to n. So let's move on. Okay, so we look at classification according to type. We mentioned classification according to type earlier, okay, in the just past card. Okay, so to determine the type of a differential equation, one should focus on the number of different variables involved in the differentiation. Okay, so we are looking at number of independent variables. Okay, so if the number of independent variables involved in the differentiation equals 1, we have it to be an ordinary differential equation. We normally also refer or shorten this as an ODE. Okay, so we normally shorten this as an ODE. Then when it's 2 or more, okay, when we have 2 or more independent variables involved in the differentiation, okay, we have a partial differential equation. Okay, so it's like this. So that one, as you might correctly guess, we refer to as a PDE. Okay, so let us now look at identifying an ODE or a PDE, how it normally looks like. Okay, if you've talked about having one different or only one independent variable, or it might have more than one, in which case it will be a partial differential equation. Okay, so let's just analyze this first example. Okay, so we can see that this dy over here, okay, it's actually the unknown function. Okay, and then the x we have over here is the independent variable. Okay, but then from here we can see, in order to determine whether it's an ODE or a PDE, we have to first look at the number of different independent variables. But over here we can see that we only have an x, that is 1. This y over here, it's actually the function itself without being differentiated. Okay, and then this is e power 3x. That's also a function, or a function of the independent variable. Okay, so we can see that this one is clearly an ODE. That is an ordinary differential equation. Okay, and then let us go on to the next example. So we have dy dt, okay, plus dp dt equaling 9p plus 4y. Okay, so what do you think will be the type of this differential equation? Okay, so let's go straight and look at it. Okay, so we have an unknown function dy. Okay, differentiated with respect to time or t. Okay, let us not jump into conclusion that it's time. Okay, it might stand for anything else. Okay, so with respect to t, so this is one independent variable. Okay, then the p, this is also a function. Okay, it's actually a function. Okay, and then we also have the differentiated with respect to t. Okay, so it's the same independent variable. It's not different. We have t and t here, they are not different. Okay, but then it's equal to 9p plus 4y. P and y, as we indicated already, okay, are functions. They are not, they are dependent variables. They depend on t. They are not independent variables. So we have only one type. So that means this is also an ODE. Isn't that easy? Okay, so we have two illustrations left. Okay, so this is dy dt equals minus 5 dv dx. Okay, we can easily get to know that y is a dependent variable, v is a dependent variable, but then over here we have t and we have x. Okay, so that tells you that t and then x are independent variables. They are two different. Okay, so there's only one conclusion, that this is a PDE. Okay, so you should take note, okay, that irrespective of the number of dependent variables, okay, our focus is mainly, as we stated earlier, okay, on the number of different independent variables. Dependent variable is not our concern over here. Okay, so we now look at a second, or the last illustration. Okay, so we have d squared u dx squared plus d squared u dt squared equals 6. Okay, so we know that this is a dependent variable with the same u dependent variable, but then we have two different independent variables. Okay, so we have x and then t, that is 2. So from our condition greater than or equal to 2, it's a partial differential equation. So we just put it over there, partial differential equation. So congratulations, you now have gone through an introduction. This is a very basic introduction to differential equation, but it's good enough to take you through. Okay, so we are now at classification according to type. So next time we'll look at the various other classifications. Okay, so have a nice time and make sure you look out for more differential equations, and then try to find out the type. Okay, whether it's an ordinary differential equation or it's a partial differential equation. Okay, so have a great time. See you. Bye.